All right, so today we're going to be talking about models of the atom. Last time we talked about atomic theory, right? We talked about protons, neutrons, electrons. We talked about the composition of the atom. And so today we're going to be talking about models of the atom. Last time we talked about what an atom's made of, right? And today we'll be talking about what the atom looks like. I've lost my clicker, so just have to do it manually. But before we get started, I'm going to pause the video and I want you to do this review problem because this is what we did. This is where we left off on Wednesday. This is an isotopic abundance question. Oxygen is the most abundant element in the crust and in the human body. The atomic masses of its three most stable isotopes, oxygen 18, oxygen 16, and oxygen 17. So that's the mass of oxygen 18. That's the mass of oxygen 16. That's the mass of oxygen 17. And I want to know what's the mass number on the periodic table without turning around and looking at the periodic table, given this data. So I'll pause the recording for a minute, give you a second to try this, and then we'll go over it. All right, let's go over this one. So this is a review problem. We did this on Wednesday. To get the mass number from the periodic table, it's a weighted average, right? Just like your grade in this class right now is a weighted average. If you looked at your grade online, I highly doubt it would be 90.00000. I mean, it might be, but it's probably not, right? Because it's a weighted average of all your grades. And so to do this kind of problem, you take the mass number times its abundance. Now notice, abundance is a percent, so we need to convert that percent to a decimal, right, before we do anything. So we move the decimal 2 to the left, because 99 and 99% are very, very different, right? Very, very different. So that needs to be moved to a decimal. Move 2 to the left, 2 to the left, and 2 to the left. And then you just multiply abundance times mass, abundance times mass, abundance times mass, and abundance times mass, and then add them up. Right? Abundance times mass. I don't have to give you this data. Okay? You can't do this if I don't give it to you. Normally I give it to you in like a table form just because it's easier to read than in paragraph form. But it's mass times abundance, mass times abundance, mass times abundance, and then you add them up. Now this is for a real element, right? Oxygen's a real element. The example I went over on Wednesday, I just made up. Breccium doesn't exist. I just made those numbers up, right? This is a real thing. And so you can check your work by looking at the periodic table, right? Another way you can check your work is your answer should be closest to the most abundant isotope, right? The most abundant isotope is 15.9949. My answer is 15.999, which makes sense, right? Over 99% of it has a mass of 15.99. So my answer should be closest to the most abundant isotope, right? So you can always self-check. If it's a real element, you can look at the periodic table. If it's a fake element that I'm just making up, you can check by looking at your answer and seeing if it's closest to the most abundant isotope, which is basically what I just said. Okay, so now let's talk about what the atom looks like and some experiments that led to those models of the atom, all right? Talk about a little bit about history, and then we're going to talk about what the models of the atom look like. So the first one we're going to talk about is called Thomson's cathode ray tube experiment. This is Thomson, J.J. Thomson. Okay, so here's the pictures from a different textbook than ours. But what you have here is a beam of charged particles, okay? And this is a magnet. So you take the magnet and you put it near the beam, one direction, it goes toward the magnet. You put it the other direction, it goes away from the magnet, right? So what are we observing? The ray bends in a magnetic field. So what do you think that means? If you've got two magnets, which two attract and which two repel? The ones that are the same, do they attract or repel? Repel, right? And the ones that are different, they attract, right? So this would be the attraction that would be opposite, and this would be the same, right? So it led to the conclusion that it's charged particles. They are negative because they're bending towards the positive end. And then these particles are found in all matter. So this was the discovery of the electron, is what this led to. And so Thomson's model of the atom, and this is something you would need to know, okay? Sketch the Thomson model, The way I recommend doing it, this is from a textbook, an easier way to sketch it. You know, if I were taking a test, I would just draw a big positive sphere, right, because the whole sphere is positive. And then Thomson visualized those electrons as being dispersed throughout, just randomly, right? So in a couple words, how would I describe it? It's a positive sphere with negative charges randomly dispersed. Right, so it's analogous to like a chocolate chip cookie. Yes? Who doesn't like chocolate chip cookies? I mean, people who are allergic to them, I guess, don't like them. But I think everybody else probably thinks the positive things about chocolate chip cookies, right? If this is the cookie, then the chocolate chips are randomly dispersed throughout. Yes? So that's how I would sketch the Thomson model of the atom. And I would need you to be able to do that and describe it in a couple words. Okay, that's what the Thomson model looks like. It's a positive sphere with negatives spread throughout. And what experiment led to this discovery? The experiment was called the ray tube. And technically, it was the cathode ray tube. But if you just put ray tube, I'd know what you meant. Cathode ray tube is what led to this. And this is the Thomson model. Okay, Thomson model. So that figure's from your textbook. This is the Dr. Bruck version. Does everybody understand Thomson's model and how that came into existence? Okay. So now I'm actually going to leave the slides. I'm going to just enter a blank slide so I can draw. Because the next one, I think it's better for me to explain it first, and then I can show you pictures, because I'm a terrible artist. I just bear with me on that. So you can suffer through my drawing first, and then you would get a picture from a book. All right, next down the line was Rutherford. Ernest Rutherford. And his experiment was called the gold foil experiment. EXPT is just shorthand for experiment. Okay, and so what Rutherford did is there was a sheet of gold, a very thin sheet of gold, okay, and then he had a radiation source, and what it was emitting was alpha particles. An alpha particle is just a helium atom, nothing fancy, okay? It's just a helium atom. And it was going through the gold, and then there was a detector on the other side, measuring where these things were going through, okay? Now, what the purpose of this test was to test the Thomson model. Okay, we're testing to see if the Thomson model is the correct model of the atom. And so here's what you would expect. Here's what you would expect to happen. If Thomson's model is true, right, where you've got this solid sphere with these negatives just kind of embedded in there randomly, right? If you have a solid sphere, well, a sphere with all these little spots embedded in, you would expect these alpha particles to come flying, and some would go through, right? Some would go on through. And others would hit and deflect, right? So you would expect a whole lot of random deflection, right? You would expect lots of deflection, right? Because the detector's over here, it's measuring where these things are going. So you'd expect some to go through, and you'd expect others to deflect off in random directions. Yes? Does this make sense based on what Thomson's model was? That's what you'd expect. But what you got was something very, very, very different. So you actually observed something entirely different from what you expect. So here's what was observed. I'll leave the middle blank. I'll leave the sphere blank, and then you tell me what you think. You got something like this. Lots and lots and lots of passing through, but then lots and lots of deflection seeming to come from one central point. Okay, interpret that data. What's the conclusion here? Are those spots randomly dispersed throughout? No, they're not. Where are they? They're focused in the middle, right? So we observed it's not random deflection, right? Deflection off a central point. What did this discover? It discovered the nucleus, right? This was the discovery of the nucleus. Okay, Thomson's model is not going to hold up to further testing, right? When you observe the data, deflection data, you see, okay, really, it's not random. There's a nucleus. The majority of the mass is located in the center, right? It's not randomly distributed throughout. It's located in the center, right? And so Rutherford's model, if we were going to sketch it, we would draw a nucleus, and then we draw electrons in random paths. Okay, so nucleus in center, electrons in random paths around nucleus. And what was the test that led to this? It was called the gold foil experiment. Okay, this is really commonly used in the world. I mean, if you go on social media today and just Google, or not even social media, if you just do a generic internet search of atom, I bet you this will be one of your top hits, right? Look at our science club shirts. That's one's got the Rutherford model on it. I think there's another one that's got Rutherford's model on it too. Yep, the one next to it from this year, it's got Rutherford's model on it. This is not the currently accepted model of the atom, right? This is not the currently accepted model of the atom, but it looks real neat. People like the way it looks, right? It's got a nice, that looks scientific factor to it. But it's not the currently accepted model of the atom. Okay? Does everyone understand the Rutherford model and where we got the Rutherford model? So now let's show you some better pictures. Right? Oh, I forgot to tell you what the problem with the Thomson model was. Right? There's the Thomson model. And the Thomson model says, well, if these electrons are distributed randomly, right, because they are, if Thomson's model is true and they're distributed randomly, well, that's a problem, because if every atom is the same, how can every atom be random? You see what I'm saying? You can't have every single cookie coming out of a cookie factory look exactly like that, right? Because they're random. And if you are truly random, then every single cookie is going to be different, right? So you can't be both random and ordered. So that was the main problem with the Thomson model. If I throw those cards up in the air, are they going to land the same time 100 times in a row? No, right? You can't have both order and disorder at the same time. So that was the main problem with Thomson's model. And that's what led to Rutherford to test it, right? So there's a picture from another textbook just showing general setup. That's what you expected to observe, right? A lot going through, a few deflecting. That's what you get. And there's another picture from another textbook, again showing what you expect, what you observe. And so the nucleus is the largest component of the atom. It accounts for the greatest portion of its mass. Just to give you some sizes here, this is not something I make you memorize, okay, so please don't think you have to memorize this. The average atomic radius, right, the size of the atom, is about 100 picometers. The average size of the nucleus is about 5 times 10 to the negative third picometers, right? So nucleus is accounting for a pretty decent chunk of the overall, when you think about the density there. So there's the Rutherford model of the atom. There's a popular television show that I will not mention by name since I don't want to violate any copyright laws, but it's a show about scientists. I'll just leave it at that. And they use this as part of their like intro and outro. When they change scenes, it shows the Rutherford model of the atom. So it's really popular, right? It's really popular. A lot of people, if you said walk up to some random stranger on the street and said, hey, draw me an atom, they'd probably draw something like this, right? But that's not the currently accepted model of the atom. And here's a big problem with Rutherford's model. Now, you don't need to memorize all this stuff here. I just want you to know kind of why Rutherford's model was put to further testing. The biggest problem is because it couldn't explain the relationship between matter and energy, okay? You know, if all matter is composed of atoms, which it is, right, then your atomic model should explain the things that matter does. And so one of the things that metals do, for instance, is when you heat them, they turn red, yes? Go home tonight and turn on your stove, it's gonna turn red if you turn it on hot, right? That's a unique property of metals. When you heat them, they turn red. Well, if that metal is composed of atoms, then there should be some sort of relationship between matter and energy, yes? But Rutherford's model didn't take energy into consideration. And then around 1900, you don't need to know this for a test or anything, just so you have an appreciation, okay? Max Planck, he just came up with a relationship between Planck's constant, which we'll talk about in general chem. Energy is equal to Planck's constant times the frequency. So it's demonstrating that energy is absorbed and released in specific little packets. And so there should be some sort of energy associated with those electrons that are orbiting, okay? Bottom line there. We're not going to go into a ton of detail about the physics stuff in this class, but if you take general chem, we'll do a lot of fun physics calculations. So the Bohr model of the atom, I'm not going to make you memorize details about Bohr's experiments, okay, because there are a lot of them and they're kind of lengthy and they're kind of detailed. So I just want you to be able to explain the Bohr model of the atom. So I'm just going to sketch it for you here. Bohr model of the atom. Again, this is a model you probably are familiar with. So you don't need to know the names of any specific experiments that Bohr did. There were a bunch, and they weren't all done by just Bohr. So we're not going to attribute it to one particular person. But the Bohr model of the atom, Niels Bohr, Bohr model. Sometimes it's called the planetary model. It takes energy into account. Okay, so in the Bohr model, you have the nucleus. That part hasn't changed. You still have electrons orbiting the nucleus, but they are in specific paths. I'm just drawing. So electrons do not orbit randomly, like Thomson said, but they orbit in specific paths, which he called orbitals. Okay? And there's an energy associated with each orbital. So this is the first energy level, this is the second energy level, this is the third energy level, this is the fourth energy level. You can tell I'm so good at drawing circles, right? I mean, If your circles look as bad as mine, that's okay. We're not here to, get out our geometric scrupulosity. So there's an energy associated with each one. The lowest energy is the one closest to the nucleus. Which he called ground state. And the highest energy, we can keep going out now. Highest energy is when you're furthest away. Okay, so there's an energy component. And also one of the things that this takes into consideration is that energy is required energy required to go up in energy levels. So if I want to go from 1 to 2, I have to put energy in. But then if I fall back down, let's say I was at 3, I put in a bunch of energy, and I went from 1 to 3. But if I fall back down, falling releases energy. Now there are components of the Bohr model that are true, okay? And that is a component of the Bohr model that is still true, okay? There is an energy component to electrons and their location to the nucleus and their energy. When we do a flame test lab in a couple weeks, so we're not going to do it next week, but a week from next week, we're going to observe this, okay? And maybe you did this in high school if you took chemistry or physical science in high school. You take a sample and you stick it in the Bunsen burner, and then you see pretty colors. So, I mean, there are parts of the Bohr model that hold true. If you add energy to an electron, it does go up in energy level. That is true. And it's not going to stay at that high energy level. It will fall back to the state it was originally. Just like if I take my 4-year-old and I give him like 15 candy bars, he's going to go crazy, right? Until his insulin kicks in and he'll come back to normal, right? So if you put energy in, those electrons will get promoted, but then they'll fall back down to where they were. And when they do, that releases energy that we see in the form of light. Okay, so that part of the Bohr model is true. Now the bit about it, it's quantitative, it's specific orbitals and a specific path and all that good stuff, that's not true. Okay, so that's the part that Bohr got wrong. So actually, I'm just going to leave this here because I've got some pictures to show you. Those are the energy levels, right? High energy versus low energy, just like being at the top of a ladder versus being at the bottom. And the main problem with Bohr's model is, in terms of the calculations especially, it only works out mathematics-wise for one electron. So in other words, hydrogen. A hydrogen atom follows the Bohr model beautifully. But once you throw that second electron in there, those two electrons start repelling each other. And it just puts your calculations out the window. Right? So in other words, classical mechanics would be like Newtonian physics, force equals ma and all that good stuff. That's classical physics, okay? You can't apply classical physics to the atomic level. That's just the gist of it. And so you don't need to memorize all this stuff. That's more of a Gen Chem kind of stuff that we get into. But you do need to know that the Bohr model, it only worked for hydrogen. Mathematics didn't support anything beyond hydrogen, which led us to the quantum model of the atom. This is the currently accepted model of the atom. There are lots of contributors, and it's not in week 14. It is in general chem, but in our class, it's next lecture. I'm going to spend an entire lecture on the quantum model. Okay, we're going to get into the nuts and bolts of it in great detail. So the quantum model is the currently accepted model of the atom. We're going to spend the entire lecture on Monday talking about the quantum mechanical model. I'm actually going to spend all next week talking about the quantum mechanical model because it's the currently accepted model. And so here's a summary of today, right? Thomson, Rutherford, Bohr, right? Thomson was the cathode ray tube. The problem was that you can't have disorder, right? It can't be randomly distributed in every single one and have every single one be the same. That doesn't work. It's either random or it's order, not both. Looks like a chocolate chip cookie. Rutherford Model, this is the one you probably see a lot. See it in pop culture a lot for sure. Developed by the gold foil experiment. There's no relationship to energy in there. Bohr Model, we didn't talk about any specific experiments, but the problem with it is it only works for helium. Hydrogen, anything beyond hydrogen doesn't work, and there's a sketch of what it looks like. So that's where we're going to stop with models of the atom. On quantum model, we're going to be doing next week. There we go. So, any questions on this before we stop? Feeling pretty good? Okay, so that's where we will stop for today.